The quiet origins of automation. Automation, in its simplest definition, is the use of machines and systems to perform tasks with minimal human intervention. Though the idea may seem distinctly modern, its origins stretch back thousands of years. The desire to reduce physical labor and increase consistency is not a recent impulse. It is a quiet thread woven throughout human history. One of the earliest examples of automation can be found in ancient water clocks and mechanical devices developed in civilizations such as Greece, China, and the Islamic world. These early machines operated according to predictable physical principles: gravity, water flow, gears, demonstrating that certain processes could be entrusted to mechanisms rather than constant human supervision. The principle was simple, yet profound. Once set in motion, a system could maintain itself. During the Middle Ages, mechanical clocks became increasingly sophisticated. They regulated time without human hands marking each passing hour. The ticking of gears symbolized a subtle shift in human life. Tasks once governed by natural rhythms began to align with mechanical precision. Automation was not yet replacing workers in large numbers, but it was reshaping expectations of reliability and consistency. The Industrial Revolution marked a decisive turning point. In the 18th and 19th centuries, machines powered by steam and later electricity transformed manufacturing. Textile mills introduced mechanized looms that could weave fabric faster and more uniformly than skilled artisans working manually. While these innovations displaced certain crafts, they also dramatically increased production capacity. Goods, once rare, became widely accessible. The concept of interchangeable parts further accelerated automation. By standardizing components, factories could assemble products in repeatable sequences. The assembly line, popularized in the early 20th century, became a defining symbol of industrial automation. Instead of one worker crafting an entire object, each person performed a specialized task while the product moved along a conveyor system. The rhythm was steady, almost meditative in its repetition. It was during this era that the philosophical implications of automation became visible. Machines were no longer merely tools, they were systems capable of structuring human labor. Yet automation did not eliminate human presence. Rather, it shifted roles, from direct craftsmanship to oversight, maintenance, and coordination. In the mid-20th century, the invention of programmable logic controllers and early industrial robots marked another milestone. In 1961, the first industrial robot, Unimate, began operating on a General Motors assembly line. It performed repetitive welding tasks in environments considered hazardous to human workers. Here, automation served a practical and protective function, removing people from dangerous conditions. What makes the history of automation particularly calming is its gradual nature. Technological change has rarely occurred overnight. Instead, it unfolds in layers: mechanical assistance, partial automation, then full system integration. Each stage reflects adaptation rather than abrupt replacement. Today's advanced robotics and artificial intelligence systems are extensions of this long evolution. They build upon centuries of experimentation with gears, levers, electricity, and algorithms. The replacement of certain human tasks with machines is not an isolated phenomenon, but part of a continuous process of refinement. Viewed from this broader historical perspective, automation appears less like a sudden upheaval and more like a steady progression. From ancient water clocks to robotic assembly lines, the story of automation is one of incremental change. It reflects humanity's enduring desire to delegate repetition to mechanisms, freeing time and attention for new forms of work. In understanding its origins, one begins to see automation not as an abrupt force, but as a slow, deliberate current flowing through history, quietly reshaping how tasks are performed and how societies organize labor. The rise of industrial robots and mechanical precision. The modern image of automation often begins with the industrial robot, a mechanical arm moving with smooth, deliberate rhythm along a factory line. These machines, designed to perform repetitive and physically demanding tasks, represent one of the most visible forms of automation, replacing human labor in specific environments. Yet, their emergence was gradual and carefully engineered. In the mid-20th century, advancements in electronics and control systems made it possible to design programmable machines capable of repeating complex motions with remarkable accuracy. Early industrial robots were primarily used in automotive manufacturing. Welding car frames, handling heavy metal components, and applying paint in controlled environments were tasks well suited to mechanical precision. These jobs often involved hazardous conditions, including exposure to fumes, intense heat, and repetitive strain. Robotic arms, powered by electric motors and guided by pre-programmed instructions, excelled in such settings. Their movements could be repeated thousands of times without fatigue. Unlike human workers, robots did not require rest breaks, were unaffected by noise, and could operate in environments unsafe for prolonged human presence. In this way, automation initially focused on replacing labor in high-risk or physically taxing roles. Precision became one of automation's defining characteristics. Modern robotic systems are capable of positioning components within fractions of a millimeter. In electronics manufacturing, for example, robots place microscopic components onto circuit boards at speeds and accuracies beyond manual capability. The consistency of such operations reduces defects and ensures uniform quality across large production volumes. Another calming aspect of industrial automation is its predictability. Once programmed, robots follow defined patterns. Sensors monitor position, pressure, and alignment, allowing real-time adjustments to maintain exact standards. This controlled repetition creates an environment of mechanical harmony, movements synchronized, materials flowing steadily along conveyors. Over time, robots became more adaptable. The development of machine vision allowed systems to see objects using cameras and image processing algorithms. This capability enabled robots to identify variations in parts, adjust grip strength, and operate in less rigidly structured environments. The factory floor began to shift from fixed programming toward responsive automation. Collaborative robots, often called cobots, introduced a new dynamic. Unlike traditional industrial robots that operate behind safety cages, cobots are designed to work alongside humans. Equipped with force sensors and advanced safety protocols, they can detect contact and slow or stop to prevent injury. In such environments, automation does not fully replace workers, but shares tasks, handling repetitive actions while humans focus on oversight and problem-solving. Automation has also extended beyond heavy manufacturing. Warehouses now employ robotic systems to retrieve and transport goods across vast storage facilities. These machines navigate using mapping algorithms, optimizing routes to minimize time and energy. The result is a logistical ecosystem where machines coordinate movements with quiet efficiency. The expansion of industrial robotics has not eliminated the need for human expertise. Engineers design workflows, technicians maintain systems, and programmers refine algorithms. As robots replace certain forms of manual labor, new roles emerge in system integration, data analysis, and robotic maintenance. The steady hum of motors and the measured sweep of mechanical arms represent more than technological progress. They reflect a shift in how societies approach repetitive and strenuous work. Automation, in this industrial context, replaces tasks rather than entire professions. It removes people from environments defined by heat, weight, and monotony, allowing human effort to be redirected toward supervision, creativity, and innovation. In observing a modern automated factory, one notices the calm regularity of motion. Materials move with quiet purpose, machines operate with tireless focus, and production unfolds in carefully balanced cycles. It is a landscape shaped not by chaos, but by rhythm. An industrial choreography where precision replaces strain and repetition becomes mechanical rather than human. Automation in agriculture and food production. Beyond the walls of factories, automation has steadily entered fields, greenhouses, and food processing facilities. Agriculture, one of humanity's oldest occupations, is increasingly shaped by robotics and intelligent systems. The transformation is gradual and methodical, blending traditional knowledge with technological precision. Modern agricultural automation often begins with data. Satellites and drones survey vast stretches of farmland, collecting information about soil moisture, crop health, and temperature patterns. Using sensors embedded in the ground, farmers can monitor nutrient levels and irrigation needs in real time. This system of precision agriculture allows resources such as water and fertilizer to be applied only where necessary, reducing waste while improving yields. Autonomous tractors now navigate fields using GPS guidance systems. Unlike earlier machinery that required constant steering, these vehicles follow pre-programmed routes with centimeter-level accuracy. They plow, plant, and harvest in straight, efficient lines. The calm rhythm of their movement reflects a shift from manual steering to digital coordination. Robotic harvesters represent another significant development. In orchards and vegetable farms, machines equipped with cameras and soft gripping mechanisms identify ripe produce and pick it carefully. Advanced image recognition software distinguishes color variations and maturity levels. Tasks once dependent on seasonal labor can now be performed continuously, day and night, under consistent standards. Greenhouses offer a particularly serene example of automation at work. Climate control systems automatically regulate temperature, humidity, and light exposure. Automated irrigation systems deliver water directly to plant roots based on sensor feedback. In vertical farming facilities, robotic arms move trays of crops through carefully calibrated growth cycles, maximizing space and minimizing environmental impact. Food processing has likewise embraced automation. Robotic systems sort, package, and label products with speed and uniformity. In bakeries and dairy plants, machines measure ingredients with precise ratios, ensuring consistency in taste and quality. Automated inspection systems detect imperfections, maintaining safety standards across large production volumes. One of the most calming aspects of agricultural automation is its role in sustainability. By optimizing inputs and reducing waste, automated systems contribute to more efficient land use. Smart irrigation conserves water, while targeted pesticide application minimizes environmental impact. Rather than expanding farmland endlessly, technology enables higher productivity within existing boundaries. However, the introduction of robotics into agriculture does alter labor patterns. Seasonal and physically demanding tasks are increasingly performed by machines. Yet new roles emerge in equipment maintenance, data analysis, and system management. Farmers become coordinators of technological ecosystems, interpreting sensor data and adjusting digital strategies. In livestock management, automation appears in the form of robotic milking systems and feeding mechanisms. Cows enter milking stations voluntarily, guided by gentle mechanical systems that operate with consistent timing and hygiene standards. Sensors track animal health indicators, alerting farmers to subtle changes that might otherwise go unnoticed. The landscape of agriculture, once defined by purely manual toil, now includes quiet machines moving steadily across open fields. Their presence is not abrupt or intrusive, but integrated into the natural cycles of planting and harvest. Automation in agriculture replaces repetitive, labor-intensive tasks while preserving the broader human role of stewardship. In this evolution, the most relaxing observation may be the harmony between tradition and technology. Fields still follow seasonal rhythms. Seeds still germinate under sunlight. But alongside these timeless processes, autonomous systems operate with calm precision, supporting food production in a world of growing demand. Automation in transportation and logistics. Transportation is one of the most dynamic systems in modern society. Goods, people, and information move continuously across cities, oceans, and continents. In recent decades, automation has begun to guide much of this motion, quietly reshaping how travel and logistics operate. One of the most visible developments is the autonomous vehicle. Self-driving cars rely on a combination of sensors, cameras, radar, and artificial intelligence to interpret their surroundings. Algorithms process data in real time, detecting road markings, pedestrians, traffic signals, and other vehicles. While full autonomy is still evolving, automated driving systems already assist with steering, braking, and lane control. In controlled environments, such as highways or designated routes, automation reduces driver fatigue and improves reaction consistency. In freight transportation, automation plays a central role in efficiency. Long-haul trucks increasingly use driver-assist systems that maintain speed, distance, and stability. These technologies aim to reduce human error, which remains a leading factor in road accidents. By standardizing response times and maintaining optimal spacing between vehicles, automated systems create smoother traffic flow. Rail networks have also adopted automation. In several major cities, metro systems operate without onboard drivers. These trains follow precisely programmed schedules, controlled by centralized systems that monitor speed and spacing. The result is a synchronized rhythm, cars arriving and departing at predictable intervals. Automation ensures that timing remains consistent even during peak hours. Maritime logistics offers another example of large-scale automation. Modern ports employ automated cranes and guided vehicles to load and unload shipping containers. Massive cargo terminals operate with minimal direct human handling. Containers are tracked digitally from ship to storage yard to outbound transport. The choreography of these operations resembles a carefully orchestrated mechanical dance, steady, measured, and efficient. Air travel also incorporates automation extensively. Commercial aircraft rely on autopilot systems capable of maintaining altitude, speed, and direction for extended periods. While pilots remain in control, automated systems manage many routine functions, reducing workload during long flights. Air traffic control systems use advanced algorithms to coordinate takeoffs and landings, optimizing airspace use and minimizing delays. Warehousing and last-mile delivery have experienced rapid automation as well. Autonomous delivery robots navigate sidewalks in some cities, transporting small packages to customers. Drones are being tested for remote deliveries, especially in areas difficult to access by road. Within warehouses, robotic systems retrieve products from shelves and prepare orders for shipment with impressive speed. The calming aspect of transportation automation lies in its reliance on prediction and coordination. Traffic patterns, shipping routes, and flight paths are mapped with extraordinary detail. Algorithms anticipate congestion and adjust routes accordingly. Data flows continuously, guiding machines to respond smoothly rather than react abruptly. However, the replacement of human roles in transportation raises important questions. Professional drivers, dock workers, and certain logistics personnel may see their responsibilities change significantly. Yet, as automation expands, new roles emerge in system monitoring, fleet management, and software development. Human oversight remains essential, particularly in complex or unpredictable scenarios. The transformation of transportation through automation reflects a broader pattern. Machines assume repetitive and timing-sensitive tasks, while humans shift toward supervision and strategic planning. Instead of gripping steering wheels or manually loading cargo, workers increasingly manage digital systems that coordinate fleets and routes. When observing an automated port or a driverless metro gliding into a station, one senses a steady continuity. Vehicles move with calculated precision, guided by invisible networks of data. The motion is smooth, almost serene. In replacing certain manual operations, automation introduces a new rhythm to movement, one defined not by haste, but by measured coordination across vast distances. Automation in offices, retail, and digital work. While factories and farms offer visible examples of automation, some of the most profound changes have occurred quietly within offices and digital environments. Here, automation does not always take the form of physical robots. Instead, it appears as software systems, algorithms, and virtual agents performing tasks once handled manually by clerks, analysts, and administrators. One of the most widespread forms of office automation is robotic process automation, often abbreviated as RPA. Despite its name, RPA involves no physical machinery. It consists of software bots programmed to carry out repetitive digital actions, copying data between systems, generating reports, processing invoices, or responding to standardized emails. These tasks, though essential, are often time-consuming and highly repetitive. By delegating them to automated scripts, organizations reduce errors and free employees to focus on analytical or creative responsibilities. In finance, automation has reshaped accounting and transaction management. Algorithms reconcile accounts, detect irregularities, and flag suspicious activity with impressive speed. High-frequency trading systems execute transactions in fractions of a second, responding to market changes faster than human reaction times allow. While human oversight remains critical in strategic decision-making, routine calculations and data processing increasingly occur without direct intervention. Retail environments have also embraced automation. Self-checkout systems allow customers to scan and pay for goods independently. Automated inventory management tracks stock levels in real time, triggering replenishment orders when supplies fall below predefined thresholds. In large distribution centers, digital systems coordinate stock placement to optimize retrieval efficiency. Customer service provides another example of digital automation. Chatbots and virtual assistants answer common questions through text or voice interfaces. Powered by natural language processing, these systems can interpret inquiries and provide structured responses. Though not substitutes for complex human interaction, they efficiently resolve routine issues and operate continuously, regardless of time zone. Automation has extended into content management and media production. Software tools schedule social media posts, analyze engagement patterns, and recommend optimal publishing times. Data-driven algorithms personalize online experiences, adjusting recommendations based on user behavior. In these contexts, automation replaces manual monitoring and repetitive adjustments. Human resources departments increasingly rely on automated systems to screen job applications. Algorithms compare resumes to predefined criteria, ranking candidates according to relevant experience and qualifications. This process accelerates initial evaluations, though it also requires careful oversight to ensure fairness and transparency. The calm quality of digital automation lies in its invisibility. Unlike industrial robots, office automation operates silently within servers and cloud platforms. Data flows through networks, processed by systems that neither tire nor lose concentration. Routine administrative burdens gradually diminish as algorithms handle structured tasks. However, the automation of digital work raises thoughtful considerations. Roles centered on repetitive data entry or standardized processing may decline. At the same time, demand grows for skills in data interpretation, system design, cybersecurity, and ethical governance of algorithms. The nature of work evolves rather than disappears. One of the most relaxing facts about office automation is its emphasis on consistency. Software follows defined logic precisely. It applies rules uniformly, without distraction or mood variation. In environments where accuracy and timeliness are critical, this reliability provides stability. Across offices, retail spaces, and digital platforms, automation steadily replaces repetitive clerical functions. Yet, human roles persist in strategy, empathy, negotiation, and creative insight. The transformation unfolds not with sudden disruption, but through gradual integration. Quiet lines of code carrying out structured tasks, while people redirect their attention toward higher-level thinking. In this digital landscape, automation hums softly in the background. It processes, calculates, and organizes with methodical calm, shaping modern professional life through invisible but steady precision. Automation in high technology and intelligent systems. Beyond factories, farms, and hospitals, automation finds one of its most advanced expressions in the world of high technology itself. In this realm, machines do not simply build physical products. They design chips, manage data networks, maintain digital infrastructure, and even assist in writing software. Automation becomes recursive, technology helping to create and refine more technology. One of the most fascinating examples is semiconductor manufacturing. The production of microchips requires environments so clean that even microscopic dust particles could disrupt functionality. Inside fabrication plants, robotic systems transport silicon wafers between processing stations in sealed containers. Precision machines deposit atomic layers of materials onto surfaces measured in nanometers. Human presence is minimal, not because expertise is unnecessary, but because the environment demands absolute control. Automation ensures stability at scales beyond human perception. Data centers provide another calm and structured illustration. Vast halls of servers process information for cloud computing, artificial intelligence, and global communication networks. Automated systems monitor temperature, power usage, and network traffic continuously. If a component fails, software reroutes workloads automatically to maintain uninterrupted service. Cooling systems adjust airflow without manual intervention. The hum of servers represents a steady pulse of digital life, sustained by algorithmic oversight. Software development itself increasingly incorporates automation. Continuous integration and deployment systems automatically test code, detect errors, and distribute updates across platforms. Developers write instructions, but automated pipelines verify performance and security at speeds no manual process could match. In this context, automation replaces repetitive testing cycles, allowing engineers to concentrate on architecture and innovation. Cybersecurity has also become deeply automated. Intelligent monitoring systems scan networks for unusual behavior, detecting anomalies in milliseconds. Instead of waiting for human review, automated defenses can isolate threats immediately. Firewalls adapt dynamically, learning from patterns across global networks. While security experts define strategies and interpret complex risks, machines handle the constant vigilance required in digital environments. Artificial intelligence itself represents a form of automation that extends beyond mechanical repetition. Machine learning models analyze vast datasets to identify patterns in language, images, and behavior. These systems automate classification, recommendation, translation, and prediction. In doing so, they replace specific analytical tasks once performed manually, sorting documents, reviewing images, or categorizing information. In smart cities, automation connects infrastructure systems into coordinated networks. Traffic lights adjust based on real-time congestion data. Power grids balance energy loads automatically, integrating renewable sources. Sensors embedded in urban environments collect information that algorithms use to optimize resource distribution. The result is a city functioning through invisible layers of digital coordination. One of the most calming aspects of technological automation is its consistency. Servers do not grow distracted, algorithms do not tire. Monitoring systems remain attentive across every second of the day. In environments defined by complexity, automation provides steady oversight. Yet, even here, human roles persist. Engineers design architectures, establish ethical guidelines, and interpret system outputs. Automation replaces specific repetitive tasks, but relies on human judgment for direction and responsibility. The relationship is symbiotic rather than adversarial. As technology continues to evolve, automation becomes less visible yet more pervasive. It operates within circuits, across fiber optic cables, and inside lines of code. Its movements are silent, electrical signals shifting at near light speed, computations resolving in fractions of a second. In this digital ecosystem, the most relaxing realization may be that automation functions as a stabilizing force. It maintains infrastructure, corrects errors, balances loads, and ensures continuity. Rather than dramatic replacement, it introduces a quiet layer of precision beneath the surface of modern life, supporting the technological world with tireless regularity.